Hello, Deepak here from Flying 101 and welcome back to another video. I'll release a weekly video related to flying, aircraft, aviation in general. And if you're interested in any of this, or if you've ever wondered about things related to flying, please click that subscribe button and don't forget to press the bell notification so every time a new video is released, you're notified. In today's video, it's back to the world of aerodynamics, and we'll be exploring a very specific and a very important phenomenon referred to as stalling. Now, before we actually get into what stalling means and what causes it, let's take a quick moment to recap how lift is generated. So for any of you who watched my previous video, you may recall this formula of lift, which is essentially half multiplied by rho, which is the density of air, so the air around the aircraft and the density of it, multiplied by the square of the airspeed of the aircraft, multiplied by the coefficient of lift, which is something we'll be discussing a bit more in today's session, multiplied by the surface area of the wings. So these are the four components multiplied by half that constitute the formula of lift. Now, that's our airfoil or the wing, and we're looking at it sideways. So we're looking at it from the side this way. And again, this is something that we covered in the video that explains how lift is created. When an aircraft is moving through air and the wing or the airfoil is subject to airflow or the relative airflow, now because of the airflow on the top of the wing having to flow at a greater speed as a result of a curvature or the camber, if you notice this, the top of the wing has actually got the curve as compared to the bottom, which is flat. It actually causes a drop in the ambient pressure or the static pressure on the top, which in turn creates the lift force, because when we have high pressure on the bottom and we have low pressure on the top, we've then got this upward force, this pull on top of the wing, and that's what creates lift. So having recapped how lift works, now let's take a moment to understand something called angle of attack. It's not as dangerous as it sounds, but basically the angle of attack is the angle between the chord line and the relative airflow. So once again, we have our wing over there. The green dotted line is a chord line, which is that imaginary line running from the front to the back of the wing, and the relative airflow, which is depicted by that blue line. So the angle to this red arc over here between the two is exactly what the angle of attack is. And the angle of attack is a very important measure when we talk about lift, because this has a direct impact on the coefficient of lift, which is one of the components for the generation of lift. Now, let's take a look at this little diagram over here, where we understand the relationship between the angle of attack, also referred to as alpha, and the coefficient of lift. As we continue increasing the angle of attack, so the angle between the chord line and the relative airflow, as we keep increasing this, the coefficient of lift also goes up, and therefore more lift is created, but it's only possible up to a certain point, which is represented as the CL max over here, the maximum coefficient of lift possible for a certain angle of attack, also referred to as a critical angle of attack. Beyond this point, what happens is the coefficient of lift drops quite sharply. Therefore, the lift drops quite sharply, because remember, the CL or the coefficient of lift has a direct impact on lift. So when this drops quite sharply, we've then got a reduction in the lift and an increase in drag. And just for information purposes, this critical angle of attack typically tends to be around 16 degrees. So we're talking about the angle between the chord line, the green line over here, and the blue line, which is the relative airflow, this usually being about more or less 16 degrees when we're talking about the critical angle of attack. Now, what's happening at this point over here? Okay, let's go back to our wing over there, which is generating lift nicely. We're in this region over here, no problem at all. Now, what's happening on the top of the wing is the airflow is flowing very smoothly, and it's got this nice boundary layer on top of the wing. So we're looking at the airflow that's going over the top, and it's flowing over very smoothly, and that's what's causing the drop in the pressure, and so the creation of lift. Now what happens is, as the airfoil or the wing is being increased in terms of the angle that it's making with the relative airflow, it reaches a point where this smooth airflow no longer happens. It no longer sustains. We've then got the separation of the smooth airflow or the laminar airflow or the boundary, and it now becomes turbulent and disturbed, represented by this blue scribbly lines over here. Once again, forgive my drawings. So once we have this disturbed air mass on top of the wing, so we don't have that smooth laminar airflow anymore, what's this actually doing? We can't have that pressure difference anymore because we don't have that smooth airflow, and that high speed air is not there anymore. And so that lift can't be created anymore because we can't have this pressure difference anymore. Remember the high pressure on the bottom and the low pressure on the top. When this occurs, lift drops quite sharply, which is the region to the right of the red dotted line. And this is exactly what would lead to a stall. Stall is purely an angle of attack problem. This is what we talked about over here. And to recover from a stall, as pilots, the thing we are trained on to execute immediately is to lower or to reduce the angle of attack. So the angle between the wing and the relative airflow, that's the immediate maneuver that needs to be executed when we are about to encounter stall or we've entered a stall. All right, so in case you're wondering, how do pilots know when an aircraft is about to enter a stall or if it's in a stalled condition? There's a couple of things. There are some physical signs that would be experienced, coupled with some warning signs that may be on board an aircraft. So the physical signs that could typically be experienced when an aircraft is about to enter a stall or is in a stalled condition is the buffeting of the airframe. So when you're talking about buffeting, we're talking about violent shaking of the airframe. So that's a telltale sign of a stall or an impending stall. Now this could be coupled with a loss of height, because remember, if an aircraft is no longer able to generate lift, it's going to start losing height. Aircraft may even have a stall warning device or a tactical feedback mechanism for the pilots. So there might be an oral or a warning system on board to alert pilots that the aircraft is about to enter a stall, and so they know that this is something that needs to be addressed immediately. It's quite a critical phenomenon, and it's something that pilots are trained to understand quite deeply, the implications of it and how to recover from it. All right, so there we have it. What causes stalls and how to recover from them. Once again, I hope that made a little bit of sense and it wasn't too difficult to follow. As always, if you have any questions or if you would like a certain topic in relation to flying, aircraft or aviation in general covered, please put that in the comments and I'll do my best to cover that in a future video. Alright, so thanks very much again for your time and I look forward to seeing you next week. Have a great day.